Okay, now we would like to move on to the parallel computation. So from the viewpoint of the users, how the parallel computation of front-eye star is carried out. So this is the content of the current video. So first I'd like to mention again about the flow of parallel computation. And I would I would pick up the same example, and I will show an example of the partitioning and how the parallel computation is done. And I'd like to get in touch with the post-processing by using the RiboCap. And also, I will check the log information. Now, here again, when you are going to do the parallel finite element of parallel finite element method of front-eye star, first you need to do the domain decomposition by using the partitioning tool. Then a whole domain is subdivided into subdomains, and each subdomain is carried out by independent processors. And that is the MPI parallel computation. Okay. So these processes are explained now. Okay, let's pick up the same example again. The name of the example is a connecting rod. You have a finite element mesh, and the boundary condition is specified like this, and material constants are set like this. Okay. So when you are going to do the parallel computation, you have a small difference from the previous sequential information, sequential computation. The difference is that you need to have the control file of the partitioning, also the shell script to run the partitioners. So you may prepare a subdirectory under your home example control rod and the PE4, and in the directory of PE4 you may have these control files and shell script to run or submit the front-eye star jobs. So the first step of the parallel computation, that is partitioning. So when you are going to run the partitioner, you need to have three input files. The first one is the general control file, HCMW control dot, and a mesh file .msh, and the third one is different. This is the information about the partitionings. So, and by using these three information or three input files, if you run the partitioners, then you will obtain the subdivided mesh files, distributed mesh files. Okay. So okay, let's take a look at this slide as an actual Unix system. it's just a typical example. Okay, and here you have an subdirectory called PE4, and already at this subdirectory you have general control file and the execution shell script. Okay, so when you are going to run the partitioner, you just submit the shell script like this. Okay, so and this, if you take a look at the inside of this file, then you may find where at which subdirectory partitioner executable is placed, or command to run the partitioner tools. Okay, and that job is managed by the job script. Then so the Unix command is a qsub. Okay. So once you run the partitioner, you will obtain the subdivided mesh like this. So since the libocap prepost, you can see the how the domain is subdivided, and the visualization file to show this picture is generated through the partitioner tools. Okay, the next step is the parallel execution of front star. So as I already explained, what you need to do, what need to prepare is general control file and distributed mesh file and analysis control file, and you run the parallel parallel front star. Okay, and that kind of process would become like this on an Unix system. So this is just a typical example. So in the subdirectory of P4, you may have the general control file and the job script which run the front star. Okay, and here I'd like to mention that the when you are going to run the front star again and again, so you don't need to have the mesh file and the analysis control file at your current directory every time. So because describing that kind of information in the general control file, you can share the mesh and the control files at common directories. Okay. Yes, once you have done the parallel computation, then this is one example of using the libocap prepost, and you read the computational results, and the stress distribution is shown like this. So this is the Mises stress distribution on the surface, and so you can see at the same time you can see the stretch of the shape, and at the sudden change of the shape, you can see the stress concentration shown in red colors. Okay, this is the last slide. Also, you can obtain the same type of log files, and if you see the computational time required to obtain the result, you can see the effect of the computational parallel computing. So here you can see that the total time is 33 seconds, and but if you remember, or if you go to the log file at the sequential computation, you may find that mostly the 3 or 4 times longer computational time was required. Okay. And parallel efficiency, in order to realize an ideal parallel efficiency, you need to consider the many other aspects, but here I'd like you to see that to some extent, for instance, in this case, if you use the 4 cores, then a 3-point certain speed up was realized.